Okay, now we are gonna do the model of a permanent magnet synchronous machine, and we're gonna start with the rotor. So in the rotor we have a permanent magnet, but we have done many models or many exercises using a one rotor. So we are gonna do our best to make the permanent magnet fit into our one rotor so we can use the same formulas. So we know that when we have in a rotor or current in a rotor, it's going to be our I alpha plus j I beta, and this is equals to our current in our phase A minus 1/2 multiplying IB plus IC, and this is for our alpha, and for I beta we will have uh, square root 3 over 2. This is our Laplace transform, IB minus IC. So this is what we know. So we are going to try to fit our uh, permanent magnet into this. So if we have three coils and we run a constant current, if we run a constant current to a coil, we are going to have a constant magnetic field. And that is basically what a permanent magnet is, a constant magnetic field. So we can say that IR is gonna be equals to this constant current. So it's gonna be IF half, yes, because half of there is gonna be this way, plus IF half, because the other half goes the other way. And IBR is gonna be minus this IF halves. And similarly, we're gonna have ICR that is gonna be minus IF halves. So now we have our analogies for our three-phase currents into our constant current into our coils. So we just need to make a fit. So whenever we see IA, we are going to say that we have IF. IB is going to be minus IF half, and the same with IC. So our IR space phasor is going to be IF minus 1/2 multiplying minus 1/2 IF minus IF half. And for our beta component, we are going to have J square root 3 over 2 minus IF halves plus, because it's minus, IF over 2. And so we have our space phasor of 3 halves IF plus 0 plus J0, which makes sense because it is a permanent magnet. Okay, so now for a stator, our voltage equation doesn't really change because it's still our three phases. So we have R1 IS plus R1 DT IS plus R0 DT IS. And we have here our rotor current in our stator reference frame. So we need to pass this into our rotor current in our stator reference frame. So we have done this before, but just a reminder, if we have here our alpha S and our beta S, so this is our alpha beta component for our stator, and here we are gonna have alpha R beta r. This is our alpha beta component for our rotor. We have between these two, we have an angle of epsilon. So if here we have what we are measuring, our phasor, then if we want to, if we have this in this reference frame, so we are going to have a magnitude and an angle here. So we have it in this reference frame, but we want to represent it in this one. So we can see that this reference frame is this reference frame if we add the epsilon. So if we want to go from here to here, we add epsilon. So from this we can say that if we have IR and we multiply it by JE, so, which is adding an angle, we are going to have our current in our stator reference frame. So applying this to this, we are going to have the 3/2 IF, that is our IR, multiplying it to the JE. Okay? And of course, all of these are constants, so we can move them here. So we're going to have 3/2 L naught IF and the derivative of e to the JE. And like that, we have our voltage equation for our stator. Now, in terms of the developed torque, we are going to have, we know that TD is 3/2 number of poles over 2 L naught times the imaginary part of the multiplication of IS times ISR. And this ISR has to be conjugated. So we have our ISR. Now, we know that ISR is going to be, it doesn't have a beta component, so we're going to get one signal, and we know that it's going to be easier if we have our stator current is shown in a rotating reference frame. So when we do our control, we see DC. We have talked about this before, and similar that we did before, we know that if we have our IS, we know that IS, our current stator reference frame, is equals to our alpha d q components of the current times if we are an angle x to j. This is just like what we did here. So if we do this, when we do our control, we're gonna get to see DC, which is gonna be easier. So our developed torque is gonna be 3/2 number of poles over 2 multiplying, oh, I'm sorry, here. So I used to write in 3/2, but it's 2/3. The formula that we developed was 2/3. Okay, so multiplying the imaginary part. So for now, we are going to say that this is our IS. And also if we do this, we are going to see that we can get rid of the angle. And we know that our IR is this, but is conjugated. So we make this negative. Okay, so now we can calculate this. Okay, So we know that this 2 halves and this 3 halves is gonna be 1, minus j epsilon times j epsilon is also gonna be 1. If is constant, so we are gonna get p over 2 if L naught, and the imaginary part of this is is cube multiplying is cube. And like this we get our developed torque formula for our permanent magnet induction machine. Well, synchronous machine. Now we are not inducting the coils in the rotor. Okay, I hope this helps.